All right. Hey guys, I'm going to start. Todd, please let me know if I should wait or something like that. I think it's just a minute past. So, all right, thank you. Hey everybody, I am going to talk about should you run your database natively inside Kubernetes? Just a quick intro. I'm Karthik Ranganathan. I'm one of the CTO and I'm one of the co-founders and the CTO at Yugabyte. And we're building a distributed SQL database. So it's just like Postgres, except it's distributed, scalable, cloud native, right? But anyways, here this is about like a lot of our users try to run databases, including Yugabyte DB, natively inside Kubernetes. And there's like a lot of ways to think about this. Should you or should you not? I think Jeremy, I think, made a comment. If the answer is no, what's the talk really about, right? Like, so the answer is not a yes or no. The answer is to give you tools to be able to answer this question on your own, assuming you want to do it or you're thinking about doing it at some point, right? So let's go ahead. And by the way, in case you guys are thinking of dropping out halfway, there's a demo coming at the halfway point, so maybe you want to stick around for that, of an actual application running on Kubernetes and so on, right? So anyways, the first thing is Kubernetes is becoming more and more popular, like, you know, whether it's the mainstream Fortune 500 companies or a lot of others trying to adopt it. And here are some pretty big companies that are like starting to use Kubernetes for, obviously everybody started out with non-stateful applications, and increasingly it's moving into the stateful side, right? Again, I won't go into it, like you folks probably have already read a lot about this type of stuff, or you're free to do so, right? The thing that's becoming interesting is over the last 4 or 5 years, you can see that the number of customers or users running Kubernetes in their environments for non-stateful and stateful workloads in production is increasing, right? And you also see that the number of actual Kubernetes clusters and pods and containers that are running in production is increasing. That's what this graph shows you. It shows you that back in 2016, we find that most of the people were running very few containers, and all the way now in 2019, a lot of people are running over 5,000 pods in production, right? So it is starting to take off. On-premise is still the most popular deployment model. I mean, and it's not super surprising because a lot of folks are trying to go from on-premise to cloud and kind of make an environment that can go to any cloud as opposed to one particular cloud, right? And it's well known that there are a bunch of pain points, but most developers, executives, operations folks are slowly converging on Kubernetes is increasingly worth it, all things said and done. Okay, so the other thing to also note is that a lot of stateful applications and databases and data products are starting to emerge and support Kubernetes natively as products, right? Like you can think of Elasticsearch, Yugabyte DB, the database that I work on, PostgreSQL, a lot of other databases are starting to offer ways to run these databases and manage them inside Kubernetes natively, right? So the question that comes up is, should you do it? What are the pros and cons? When should you do it? When should you not? How should you think about this? Right? So let's jump right in, right? Like there's two parts to this. There is you should do it for some reasons, and you shouldn't do it for some reasons. And then in this talk, we'll first look at why you should do it, what are the good things it brings you, and what are some of the gotchas there. Then we're going to look at why you shouldn't do it, and what are some of the gotchas there. And each user, each environment, each organization is unique. So you'd have to make the decision based on what works for you, right? So there's obviously not a clean yes or no answer. Let's keep going. Okay, so the first thing to note is that Kubernetes actually helps you do better resource utilization, right? So as the diagram on the right shows a bunch of different nodes, each with different sized databases, and this can be size as it relates to memory, as it relates to CPU, disk, a variety of other things. And Kubernetes helps you pack these better across nodes, way better than we could do it ourselves as humans, and keep them dynamically up to date. Like you add a node, you remove a node fails, it'll figure out how to redistribute all of this in kind of an optimal manner, right? So that means your nodes get better utilized and you reduce the cost, right? Your overall cost, as opposed to running each of these on a separate VM and figuring out how to keep these VMs up and running and optimal, right? It's typically also very useful, as in this diagram, when you're running a large number of databases. And so this could be when you're doing a multi-tenant type of application where every user or your customer has a separate database for themselves because they're doing complex things, and you want to size them according to the usage. And this is also useful if you're doing a self-service private DBaaS where somebody comes in and wants a database of a certain size, and they just specify it, and they're able to get that database, work with it, and give it up once they're done, right? So this fast cycle of create me a database, I'll use it, and I'll tear it down. Right? But one of the things to watch out for, specifically if you're running, business critical workloads in production in this type of a model, is just watch out for the noisy neighbor problem, because these pods keep moving around and they give you a lot of isolation and good properties when it comes to CPU and memory, but the disk is still a finite resource, right? So you could have one person, or even the network for that matter. So one database or VM or user could end up, causing unnecessary effects on other databases, independent databases for unrelated users that are sitting on the same node. So pods that sit on the same nodes can, affect one another in some way, right? And the other aspect to this is also you typically want to use Kubernetes, especially in self-service scenarios where you can allow the CPU to burst, right? But we all know from the VM side of the house that if you do oversubscription of your CPU, you'll get into trouble. You can just do that much more easily in Kubernetes. So that's another thing to watch out for. All right. The second advantage of running Kubernetes is that you can resize your resources dynamically, right? So you don't have to really do anything complex. You don't have to incur downtime. You don't have to do a painful migration. So think of this as you can just scale your database by just applying a couple of requests which say, look, increase the number of CPU or the CPU limit that this application is allowed to go to, or increase the memory, or in some cases even increase the disk size, right? So you're able to do a whole bunch of dynamic scaling using Kubernetes, which is actually a really good property, right? And that makes it really simple and efficient. A third piece that makes it very attractive, as we talked about, is a lot of on-prem deployments today, but with the intent of going to a cloud or intent of some portion of that application going to the cloud. So it does give you portability between cloud and on-premises. And the first thing that helps this a lot is your infrastructure is written as code, so you can take this code to any cloud environment and get it deployed. And it works pretty much in a similar fashion on most clouds, right? And if you go to clouds, you can also leverage the fully managed versions of Kubernetes, like AKS, EKS, GKE, right? From the big three cloud providers, and there's a whole bunch of other managed Kubernetes options. There's also the ability for you to roll your own self-managed Kubernetes, which looks identical to your on-prem deployment on public clouds on VMs, right? So there's a whole bunch of options here which make it look similar. But however, one thing to note is that while it is true that the broad strokes of architecture and how you lay things out are the same, it's not perfectly portable in the sense you still have to understand how things work in the cloud. Like, for example, you have load balancers or volume types, and whether they're persistent volumes or NVMe or locally attached, or how you place stuff in various node pools. All of these kind of like the details actually could differ from cloud to cloud, and those are things that you'd have to be aware of, right? So, but it does a good job. It gets you most of the way there. So while it's something to watch out for, and these are not necessarily deal breakers in any sense, right? Because it does achieve a large part of what it promises to do. The other very nice property is the out-of-the-box orchestration. So if you have a pod that fails, it gets restarted automatically. If you add a node to a cluster of Kubernetes cluster, it figures out what pods to move and automatically reallocates those pods and reaches an optimal resource utilization based on some policies. And all of these policies that you want in order to redistribute pods to other nodes, like I'll give you an example. You may have a policy where two databases must not live on the same node, for example, right? Like you could specify this as an AntiAffinity rule, and you can specify it in code, right? And doing so allows you to just encode the rules you want enforced and just let Kubernetes do the rest of the stuff, right? Otherwise, you'd have to be doing it manually, and it kind of gets hard to do at scale, right? And now some of the things you will lose are, like, for example, those of us that have run databases on VMs, you might want to try out a change or configuration knob, something on one of the VMs, and just see how it works out. And then you come back and say, look, this is working out really great. Let me go and make the change on all the VMs, right? Now, it's a good thing because it gives you the convenience, flexibility, and the speed of achieving that. But it's a bad thing because, then configuration starts drifting from the master copy. So it's a mixed bag, but sometimes it is useful in a pinch. This is something you will not be able to do very easily inside Kubernetes, right? You wouldn't be able to go into a pod and replace some config nom and just expect it to work, because if the pod moves elsewhere or gets restarted, then you would lose that configuration. And so, but I would say this is actually more good than bad because it forces good practices, but it does lose the flexibility and the last minute agility. The other bit is around automating day two operations. Kubernetes gives a great framework using the operators so that you can make the operational stuff really easier. And you can pretty much codify things like how do you do periodic backups, or how do you upgrade the database, the runbook for that, or if you want to do security patching on the database itself and the AMI refresh when you get on the actual OS that you're running on. So all of this gets easier to automate. So that's a big, big plus. Though one thing to watch out for is when doing any of these automated automations, including things like, for example, your software upgrades or your security patching, or even like if you have a replica, like you have a main RDBMS cluster and a node and a replica pod, doing the failover between these, you should always watch out for will you lose data and what is the, because it's async replication, and what is the implication of losing data, right? So it's important to think about it, because when we do it as people with operationally, we tend to look at a few things and make sure, hey, is the cluster running okay? Is the load too high? Are we in some peak setting, and so on, right? But if you just automate it without thinking through all of those scenarios, then you can get into trouble, because it might just happen at a suboptimal time, and it might amplify, like, some pain point that you don't want to hit. Anyways, that's something fully under control, though, but that's something that you can do and think about. And a mitigation here is to use a distributed database where the data is inherently replicated, and you don't have either problem of data loss or of downtime or unavailability because this thing is failing over, or et cetera, et cetera. Okay, so that concludes the first section on some of the reasons why you would want to do it. Now let's look at the second section on why you would not want to run a database in Kubernetes, right? So it's really the trade-offs that matter. So every decision, I guess, in life, but specifically in infrastructure, always has a trade-off, right? So let's look at what are the trade-offs on the other side. The first thing to know is that there is a greater chance of pod failures compared to when you deploy a database on VMs or bare metal, right? And that's because the pod failure happens for many other reasons compared to why a VM failure would happen. For example, right, like every pod, its life cycle is tied to the process that's running, right? And let's say there's a query that comes in that your database is not able to handle very well, and there's like a bad configuration, and that takes the database down, right? It takes your pod down as well, and your entire pod restarts, right? It restarts quickly, however, but nevertheless, your pod does fail, right? And similarly, you have out of memory and bad configuration on the pods where you're using oversubscription on memory, and sometimes you run out of memory. Then you will have the own killer come in and kill your entire pod, and your pod goes out and comes back, as opposed to just your process, right? And similarly, if you add a node, you could just have transparent rescheduling of pods, which will take down pods. So there's a number of reasons why in this dynamic environment, pods can go down and come back up elsewhere. And I think it's very important to think through if this will cause either disruption to your service, like for example, if your database goes down, will it take it a while to recover and actually come back up? Because the pod coming up doesn't mean your database is running. Your database has to recover from that crash, right? Like after it died. And so is your database running in such a way that it's going to take a while? The second thing is also, as we talked about before, to think about, is there going to be data loss? Like specifically, if you have a replica for this pod, and if the pod goes down and your database is taking a while, and your automation kicks in and promotes your replica, now you're into a situation where you could lose some data, right? So these are some of the things, again, to think about. A mitigation here, again, is to use a distributed database, because you're guaranteed that even if there's a pod failure, you're not going to lose any data. Local versus persistent storage is another important aspect to think about. Local storage is when you run your database on a pod and it uses the disk attached to the actual VM or node that the Kubernetes, that's part of the Kubernetes cluster, right? So so that means that all of the data is stored on that local disk, right? And if the pod dies and moves to a different node, your data is lost because it was left in the previous node, and there's no way for the new node to actually reference the old data. Now, then you might ask the question, why does anybody ever want to run local storage, right? If persistent is actually going to replicate this data and make it available anywhere you go. So with persistent disk, if the pod in this example moves from node 1 to node 3, your persistent disk actually gets pulled from node 1 to node 3 as well, and you see the same disk. With local, however, it's whatever you wrote locally, so you may not have the data, right? Now, the advantage is if you have NVMe drives and you want to run locally with very low latency, this is actually a great deployment model. However, you just have to watch out for what happens after a failure. The second bit is persistent storage. While available in cloud providers like AWS, GCP, etc., they just give you abstraction to where you just ask for a persistent drive, which is remotely replicated of a certain size. It's not that easy for on-premise deployments, right? So there's some complexity here. You have to use a software solution. There's a number of them, like there's OpenEBS, there's Portworx, there's a number of solutions that you have to use. And now that brings up the question, is the performance or the characteristics of one of these the same as what one of the cloud providers kind of give you, or you could map it to an external NFS mount or so on. So there's a lot of different options, each of them with their own pros and cons. So it generally is a little more complexity. Alternatively, if you're using a distributed database, again, this doesn't matter because the database replicates the data itself, right? So these are some of the reasons why distributed databases actually make life a little easier inside a Kubernetes environment. However, it really depends on what you're trying to achieve and what you're doing with the database, right? So it might not strictly be necessary. Okay, so the next bit, and this is actually a really sticky one, is the need for a load balancer, right? Like now a Kubernetes cluster or pod, actually a service has restricted ingress, right? So it'll force you to declare how you want everybody to access the pods within it. And it doesn't really expose the details of any one pod because it's an abstraction as a service abstraction, right? So if your application is not running in the same Kubernetes cluster, chances are and that means your application can be running in a different Kubernetes cluster or it can be running outside Kubernetes, it doesn't matter. Chances are you likely need a load balancer of some sort to expose this database to your application, right, externally to anybody. And this is typically not an issue in the public cloud deployments because you can use the cloud provider provided network-based load balancers. Like all of the big public clouds have it, and they have very clean abstractions to say, just give me a load balancer, make it some property, etc., etc. But one caveat to note is like you may want this public load balancer to have an elastic IP or a public-facing IP or various different requirements, and there could be limits based on exactly the cloud on how many such load balancers can you deploy and how many public IP addresses or elastic IPs can you get, right? Like the static IPs can you get, right? So there's a bunch of restrictions there. So if you're going that way, just watch out for those. But otherwise in the public clouds, this is really not that big of a deal. On-premise though, this is actually much more complicated because you now have to think about software-based load balancers that work well inside Kubernetes, or like the FI or hardware-based load balancers, and how many of them you can come up with, and so there's just a bunch of complexity around how you reach your app. Right? Now you may be tempted to say at this point, hey, why not I just throw all my apps inside the same Kubernetes cluster and just run one giant cluster, right? So that is actually not necessarily a good practice. It's better for you to run many small Kubernetes clusters to restrict the size of correlated failures or the extent of correlated failures. So it's just better to get into the habit of running more smaller clusters than one larger cluster. So depending on, again, what you're trying to achieve this and where you're trying to achieve it, the load balancer could be an issue you might want to think about. Okay, the next bit is something that's surmountable, but again, not, if you're asked a year ago, this would be, again, a deal breaker, a very hard thing a year or two ago, but now it's increasingly getting surmountable, but it's still complex, right? It's about how you get replication across two different Kubernetes clusters. Like a Kubernetes cluster is typically local to a geography. Let's say you want to do east-west replication across the US to make sure your data is redundant across regions, right? That means you do something like as shown in the diagram on the right, which is you have a database deployed on the left, which is US West, and you have another database on the right, which is US East, and you want to set up either unidirectional or bidirectional replication between them, right? And so the issue here is you cannot get the pods inside one cluster to very easily refer to, which is discover using a DNS name something, the pod inside the other cluster, and nor can you easily get it to talk at the IP TCP level, right, in order to replicate data. So this makes it immensely challenging to figure out what you would do. Now, I'm not saying that you can never do it. It is possible, but this is a very craftsman kind of solution. In for example, GKE, you can use VPC peering between the Kubernetes clusters to make them communicate at the IP address level, at the private IP level. So you can actually achieve this. But if you go to AKS or EKS, you cannot, right? And if you do it on-prem, it really depends on your networking. And it depends on details like, do you have a layer 2 or a layer 3, or at what layer do you have the addressability, right? So different layers have different issues. So what do you do if you want to overcome this type of thing? You can do DNS chaining, where you take over the responsibility of exposing these IP addresses and pods externally, and figure out whether you're going to put ingress points for each of the pods and egress and ingress points for each of the pods, and so on and so forth. Or the other option is to use a service mesh like Istio, right? Now, each of them has their own trade-offs. If you're using DNS chaining and a whole bunch of these type of services in order to achieve what you want, it is going to be more complex. You have to really understand the landscape. It's a whole bunch of newer projects that are emerging really fast, like is Calico, and you might need to use BGP and a whole bunch of things together in order to get all of that to work really well. So there's a little bit of solutioning and maturity after the solutioning that needs to be done. And the other option is to use something like Istio, like I said, as service mesh, but it typically cuts down your performance because the service mesh works at the HTTPS layer, which is the highest layer 7, as opposed to the TCP layer where most of the databases want to replicate, right? So that means you're masking your TCP and slapping on headers all the way till it reaches the HTTP layer, and then replicating it, and then traveling down all the way down to the TCP layer on the other side, right? So there's just a couple of things to watch out here, right? So if your predominant deployment is heavily multi-region, then really think about it. Are they all the same type? Are they different? Like, et cetera, et cetera. Okay, the last bit that I want to call out is the operational maturity curve. If you're running databases, at least databases that you care about in Kubernetes, then you should be ready to go all in on Kubernetes. Like things like we talked about before, where run many small clusters instead of one large cluster to minimize the correlated failure probability. And you should know a whole bunch of things about how Kubernetes works, right? So there's all of these gotchas. Like, it's not really gotchas. There's more like stuff you need to know. But like, I mean, you could think of, these are buzzwords that if you don't know about, you probably shouldn't be running your database in production in Kubernetes. But things like, what is anti-affinity, or what is a pod disruption budget, or what are sidecars, or how do you achieve observability with Prometheus, which is metrics monitoring, scraping, and that whole 9 yards on that side. Or how do you troubleshoot with cookbooks? Like, for example, if you have a crash back-off loop, what do you do? How do you detect memory oversubscription, or like when your services are crashing or dying because of memory pressure or things like that? What is your story around private image repository registry and your pull secrets, and who can upload and who can download and who has what permissions around it? And so you just need to know, this is just a sample, right? But you need to know all of these things if you're getting serious about running business critical applications and databases in production inside Kubernetes. Right? So again, not meant to scare, it's just meant to inform, right? Like I said, the answer is there are a lot of people running it successfully, and it's the right thing for them. But if you're thinking about doing this, for whether you're already doing it or whether you're newly venturing into the territory, it's still good to go through some kind of a mental map or a checklist of what are the things to think about. All right. So we talked a bit about mitigations, and distributed databases came up, and we talked about RDBMSs and distributed databases. So like the first thing to note is Jeremy comments is speaking to his soul. That's great. So anyway, so traditional RDBMSs and distributed databases, right? So let's take a look at what the trade-offs change to, right? Like and we'll talk about an example of a distributed SQL database. Is, for example, Yugabyte DB, right? So the first thing is, if you just look at a traditional RDBMS, the stuff on the left in green is generally good. Again, we talked about some caveats, like, in each of these cases, we said like, hey, portability is great, but it's not 100%. We said resource utilization is great, but watch out for noisy neighbors. So there's always caveats, but that's the stuff on the left, which is the good stuff, right? The stuff on the right, there's two parts to it. There's red and there's blue. The red is, if you cannot deal with that stuff, don't do it, right? Like, it's actually not really easy to solve. And the stuff in the blue is, like, if you might be able to mitigate and work your way around it, right? So if you're running in a traditional database, like a PostgreSQL, like you get all of this stuff on the left, right? That's absolutely true. On the right, though, you do have a greater chance of pod failure. So you either know that it's okay or you have a way to deal with it or not, right? And if not, then you should probably stay away from it. And do you need local storage versus persistent storage? And do you have persistent storage? If the answer is no, I don't have persistent storage because I'm on-prem, or no, I need the latency characteristics of an NVMe drive that's locally attached, then it might not be the right solution for you if you're using PostgreSQL, traditional RDBMS, right? But the load balancer, the networking complexities, and the operational maturity curve doesn't matter. If you're doing it, right? You need to find a way. If you don't have a load balancer solution, it's probably a deal breaker. But if you do, or if you have other ways to solve it, that's fine. If you go to a distributed SQL database like Yugabyte DB, and we'll talk a little bit about what Yugabyte DB is. I don't want to spend too much time on it. But what do you get back, right? What makes it a little more interesting to run this in Kubernetes is the fact that all the stuff on the left remains the same, but you don't have to worry about the greater chance of pod failures, and you don't have to worry about local or persistent storage because the database replicates the data by itself, right? And it is highly available, and it can do stuff at the database layer. So that means you're still stuck with figuring out how to access data on the load balancer, figuring out networking if you're doing multi-region, multi-Kubernetes cluster deployments, and your operational maturity curve. There's no getting around those, but at least it can take away some of the core pains, right? And of course, your app has to be applicable to be running in some of these distributed SQL databases. So that's the trade-off to think about, right? So we talked about Yugabyte DB. So just a quick note on what it is. Yugabyte DB is a fully open source database. It's transactional and it's distributed SQL, which means it can run on a cluster of pods or nodes and replicate data by itself. And that's the way it actually is resilient to failure. So when one pod fails, another takes over in a matter of seconds. And so you always have high availability. And you can always add more pods to get the data spread out and the queries spread out on a greater set of CPUs, right? And so you're able to achieve resilience and scale quite easily from your Kubernetes cluster, right? The upper half of Yugabyte, even though it's distributed across a set of pods, is actually Postgres compatible. So if you just throw a load balancer on top, you can hit any node on the cluster, and it's going to distribute the query processing as well. So it actually is, it works quite well in tandem with Kubernetes, assuming that some of the other things we talked about before, like the load balancer and the other things, like your operational maturity and all of that actually works out there. Okay, so here's a quick comparison between Yugabyte DB and Postgres and Google Spanner. So Postgres has a good set of RDBMS features and an ecosystem. Yugabyte retains those, so that means your stored procedures, triggers. So mostly anything that runs on Postgres usually runs on Yugabyte. Like there's a good set of coverage, and there are some features we're still adding to complete the coverage. So anyways, the idea is to be able to support most of the Postgres set of features, while the availability, scale, and the ability to perform transactions that are distributed is actually built into the database. So we actually do have deployments where folks have deployed Yugabyte DB to stitch 3 different Kubernetes clusters together to get a replication factor 3 cluster on top of 3 Kubernetes clusters. So we are able to distribute transactions quite well. But again, getting that to work and getting that to work in production, right? 2 different things. So, and that's where the most of this talk is coming in, right? The other thing about data replication is with Yugabyte DB, we felt that asynchronous replication is as important as sync. So you can create 2 clusters and have them asynchronously replicate to each other, right? So the idea is to give a flavor of Postgres that works well in a cloud-native environment like Kubernetes. So this is really the aim of a database like a distributed SQL database like Yugabyte DB. And as you can see, what we really do is take out those 2 reds, but everything else still stays on the table. So it's not like it's like a 100% slam dunk. Okay. Okay, so I think Mustafa says he tried running 3 projects on Yugabyte and didn't work, even run migration, so it's not compatible. I think we'd love to work with you, Mustafa. If you can drop into our community Slack or write to us or open a GitHub, we'll take a look at that. Again, we're adding more and more support for it, so depending on the version and what's coming down the pipe, there may be some things you may have to work around in the short term. Right? Okay, so this is how Yugabyte works at a high level when deployed inside Kubernetes. So you have a query layer and then a storage layer. This is an internal split. The query layer is actually PostgreSQL's query layer, the upper half. and the lower half is a replicated distributed storage layer. And you don't even know that because it's just running as a single pod. It's all running in a single pod. And so these services run across multiple pods, and they replicate data, and they use the local store on each of the pods. So your app can connect to any node, and therefore putting a load balancer on top of this actually works really well as long as it sprays your queries across the nodes and evenly utilizes the entire cluster. Okay, so now that we talked about some of the caveats, right? We said, hey, local store versus remote storage and all of this stuff. Let's actually look at what you get with a database like Yugabyte DB, where we removed a couple of those restrictions, right? So the first thing is you can use local storage because it has Yugabyte DB performs the replication synchronously at the database layer, which means there are two different there are three different pods, each writing the same data in their local disk. So if any one dies, there's others that can take its spot. And so that means you can actually use a locally attached NVMe for low latency applications inside Kubernetes natively. So that restriction does go up. However, there is still a case for remote storage or the persistent storage where you have, even though you have slightly higher latency, it's not a whole lot higher in the case of, for example, EBS, but it is higher. And you get a slightly lower throughput because you now have to replicate, and your bandwidth is kind of, the disk bandwidth depends on how much replication you can do and how quickly can you do it. But the advantage you get is that you get higher storage resilience. So specifically, if your data is spread across different geographies or different Kubernetes clusters, then you don't have to re-replicate from another cluster. You can rebuild your data on failures locally because it's resilient. The second piece where remote storage is useful is you can put larger disk sizes, right? Like NVMEs come with pre-cut disk sizes, like you get so much of disk per node, and that's it, right? But with remote storage, you can actually size the disk according to what you want on the node. The second piece is as I had promised, if folks don't know what AntiAffinity is or what pod disruption budgets are, it's probably a bad idea to just go into production inside Kubernetes. But anyways, AntiAffinity is some of the rules that you can specify where you say two pods should never run on the same machine, right? Why do you care about it? If you have a RDBMS and you have a replica, you don't want both of them to run on the same machine, because if the machine goes down, you lost everything. You lost both your working database, the master, as well as the replica, right? Which is not a good idea. So the idea with AntiAffinity is you can tag those two pods or that service, which is the serving the read-write database and the read-only replica or the standby. You can tag them to say never put them on the same node, right? Now, Yugabyte DB replicates data at its own layer, so it's not you setting up the two sides, it's the database doing it internally. And so you want the different replicas to never place data on the same node, right? So this is something that we achieved through pod AntiAffinity rules, and that we're able to specify, right? And we also use a variety of different schemes to make sure your data can get a copy of your data exists across zones, across nodes, across regions, right? And so on. So there's a whole bunch of pod label matching and a lot of stuff that goes on. Again, happy to take it offline, but anyway, so these are some of the things that we're able to implement natively using Kubernetes. Some of the other things that, and just notes on some of the other things, right? Firstly, the node failure is kind of transparent to whether it's a local store or a remote store, because the database can replicate data if it's a local store. But the caveat here is don't upgrade it so quickly that all your nodes shuffle. So you need to give time for the database to re-replicate the data to the new location, right? So as we said, when a pod moves from node A to node B with local storage option, your data needs to get replicated from somewhere to the new node, node B, right? And this is done in Yugabyte DB automatically from other replicas. However, it takes time, so you just have to make sure that we give it time. Similarly, for rolling upgrades, you can go one pod at a time and upgrade the software, which is effectively upgrade to a new version of the pod, right? Like you go to a new version, and if you're using persistent drives, the old drive gets remounted. If you're using local, and your updates will mostly restart your pod on the same node on the same machine, right? So you don't lose data in this case, and you don't have to rebuild it. Data resilience, I mean, Yugabyte DB can do a distributed snapshot inside a cluster, so that usually, and so the snapshot restores are usually fine, and you can roll back your cluster or restore into a new cluster for point-in-time recovery for enhanced resilience. Okay, so I think there's a question from Stephen, and by the way, there's some questions in the Q&A tab. I'll take a look at it momentarily. If your anti-affinity pod policy is multi-region, multi-zone, then is that implying it's all in one K8s cluster? No, it's not actually. We can do, if the K8s cluster is capable of stretching to multi-region or multi-zone, then we can do that, but that's not the case. A GKE, for instance, can do a multi-zone single K8s cluster. Other folks cannot. And multi-region, no one can. So I think the bottom line is we do this either as 3 separate Kubernetes clusters, one in each zone or each region, or in some cases when the Kubernetes provider itself can offer multi-zone single Kubernetes cluster deployment, then we can just natively use one Kubernetes cluster to place data across. So the reality is it's 3 clusters most of the time. In some cases, it's 1. Okay, so this is just a quick how do you take it forward from here kind of thing, right? So like, for example, you can build an operator that detects that all pods are running at 80% CPU or whatever, and then just Kubernetes can detect this, and you can automatically say, hey, wait for a minute. If everybody is over 80% CPU, then just add a few more pods and then wait again, and keep doing this until you hit a max amount, right? So this can help you implement, and you can do the reverse. You can say, hey, observe everybody. If they're less than 50% or 40% for a minute, then decrease. And I think probably a minute is a bad idea, but you get the idea, right? So observe it for a little bit of time and then shrink or expand the cluster as needed. And so with a database like Yugabyte DB, you can put this rule in effect along with the database's native scale, and you'll be able to achieve scale out and scale in. Okay, so now we're going to jump into the cool part, demo as promised. So let's go into an e-commerce app. Let's actually look at a real app, and then if this was a live thing, I would have asked folks to guess what are the pieces of the stack. Maybe folks can still write it in the chat. There's a good conversation going on anyway. So the app is as follows, right? We'll take a look at it, but it's a marketplace app. It's like Amazon.com, for example. You can browse and buy millions of products. If you get to even look at ratings and reviews and effectiveness, order your products, check out, so on and so forth, right? So we're going to take a look at this app, which is all running in Kubernetes. So it's a full stack running in Kubernetes. And if you guys can throw in there, what are the pieces that you think went into building this app, that'd be fun. And then we can talk about what we really do. So here's the app. So here's the app that's running, right? So it's just a marketplace app with a whole bunch of different categories. Again, it's very simple. There's like a whole bunch of products, right? So and you can say like, what? Okay, let me go to, I like bestsellers, healing, music. You can go in here. You can say I want to add this to cart, right? And you can say, look, there's something here. I'm going to check out this item from my cart, and it just simply checks it out. Right? So very, very simple app, except you may want data to be close to users. You may want to be able to handle scale. You may want to be able to handle failure. So you may have a lot of stuff under the hood while keeping the transactional nature of the app, right? So if there are any takers, just drop it in the chat session. Otherwise, I'm just going to go ahead and tell you guys what goes on behind the scenes. And how that maps to everything that we talked about before. So, like this is the stack. Looks like there were no takers. Anyways, everything running inside Kubernetes. It's Yugabyte DB and then Istio, which is a service mesh to talk across different Kubernetes clusters. And then you have Spark, which is actually deployed inside in order to compute the ratings of items, like where you want to say, hey, let me look at all these items and what people are buying or the reviews, and kind of compute the top rated items. And there's React for the UI, and it's Spring as the middleware, like exposing the REST API. And all of this is deployed on top of Kubernetes, right? There's a GitHub that you can go look at if you guys are interested. So let's look at how this works, right? This is the rough architecture. The UI, which is actually, the UI, which is actually running in your browser, talks to an API gateway, which is built out of Spring. The API gateway has 3 microservices. There's a product, there's a checkout, and there's a cart, right? They do obviously whatever the names mention, and they use the various APIs to talk to a Yugabyte cluster, which is attached to Spark behind the scenes, right? So this entire thing, the UI obviously runs on your browser or your cell phone or whatever it is, but everything else, right, like behind the UI actually runs on inside Kubernetes natively. And so you can scale any one of these services really quickly to make sure you're able to keep up, right? Again, just a quick point on Istio. Istio is actually used in this case to do traffic management between the microservices, right? So, and how do you get each of the microservices to talk to each other, as well as in certain cases, like we talked about, if you want a geographically distributed deployment, you actually want Yugabyte to use Istio in order to talk to the pods, right, between. So this is a deployment scenario where you may want this app to get scaled out geographically. So you may want Yugabyte DB to actually use Istio to be able to talk to each of this is a different Kubernetes cluster, and you want Istio to do the traffic routing between these and Yugabyte DB to use them. As we said, like this is something that's a pattern that applies to most Kubernetes deployments, but the downside here is your performance, right? Like obviously it's going to go all the way up to layer 7 HTTPS and then come back down to whatever layer, right? So, okay. So some of the things to keep in mind if you are doing, multi-region deployments is that typically we expect pod-to-pod communication. That's the fast path or the performant path, but you can put ingress points, load balancers, and everything, but each one of those introduces another network hop, and therefore slows down the overall performance of the database. You need a global DNS resolution system so that different pods in different Kubernetes clusters can discover and talk to each other. You need the ability to create localized load balancers in each of the regions. You need all sorts of RBAC control to make sure you're able to allow the various pieces to work, right? And so you can actually take a look at this type of a deployment architecture where you can deploy Yugabyte DB on a multi-cluster GKE and Yugabyte DB's documentation, right? So just something if you're interested in. Yeah, if you made it this far, awesome. Thank you, everybody. I think I'll look at the Q&A tab too, but we're a fast-growing community. We're a completely open source project. So, join us on our community Slack. A lot of interesting discussions going on, including about deploying distributed SQL databases inside Kubernetes. It's yugabyte.com/Slack. We'd love you to join our community and be a partner. Let me look at the Q&A tab to make sure I didn't miss anything. Okay, I did. Okay, Emerson asks, just to be clear, is it the database instance on one pod in one cluster that's unable to replicate to a database instance on one pod in a different cluster? Yes, that's right. So that's because the database instances themselves, the databases can, right? In VMs, you just have databases on two different VMs in two different locations, and they simply talk to each other using TCP. If you now replace your VM with a pod inside a Kubernetes cluster, one in each side, they cannot talk to each other because the IP addresses are masked, and it's kind of like a private LAN, right? Like a private network. So you need these private networks to get bridged in some way, and that's the complicated bit. Okay, so UA says you can replicate cross-KHS clusters as long as the pod IP from one can be resolved from the other. Yes, that's right. So this is network resolving can be done using iBGP and eBGP. That's absolutely right, UA. I was just mentioning that you have to figure out where you're deploying it and if you're willing to take on all of that stuff and so on, right? So it's like Calico and BGP, and there's a whole bunch of things that you can use in order to get this done by yourself. And there are certain, like for example, GKE gives native peering of IP addresses, and you can just take care of the DNS yourself, right? So there's different ways to do this depending on the substrate Kubernetes. But anyways, these are just some of the things to keep in mind. Other questions, folks? I think it's open floor. That's mainly what I had. So happy to take more questions if people have any. Welcome, folks. Welcome, Stephen. Welcome, Emerson. Really appreciate you guys enjoyed it. Thanks, Sean. Thanks, everybody. Like I said, feel free to join us on our community Slack, yugabyte.com/Slack. Sorry, there's a question. Any comments on XtraDB cluster versus Yugabyte? I don't know what XtraDB cluster does, to be honest, properly. So I don't have an opinion. I can take a look and come back. Yeah, so it's the best I can tell you. Sure thing, folks. And like I said, any questions, would love to hear from you folks on Slack or Twitter or anywhere. Just grab me anywhere. Cool. I know we're a few minutes early, Todd, but yeah, I typically do 40 to 45 minutes, so it went by like really quickly, I guess. Yep, all done. So we can wrap up. Thanks, everybody. Thanks a lot.